Yes, just wait 1 or 2 more minutes. Just waiting some of your classmates to arrive. The goal of today, we will cover the regression, linear regression. Already covered half of them, and then or almost half of them, and then we will cover the remaining next week, and then we'll finish everything in this course. And the 19 is I guess we can't have class because of it's a graduation ceremony, so we can't have class. But we'll think about what to do. But that day we don't have class because afternoon will be I guess it would be no class, right? So that we cannot have class. Any question you can raise at the moment if you have any. Just wait 1 or 2 more minutes, then we'll start. There are some questions. Will we have other quiz soon? Not today, because probably you may have missed it. Is the quiz will be after the linear regression and the quiz because of we lose 1 class due to congregation on the next Thursday, so that's why we have to figure out what to do. I mean, so we will combine 2 quiz. And someone asked me the assignment, I think assignment 3. I need to check the assignment. Pick up the assignment 3 first. I don't know where's my assignment 3, but maybe let me go to check my. So someone asked me assignment 3 about question. Okay. Assignment 3 about question 7B. So it's 6.8.65. Meeting the requirement. You should be reading the question carefully. Meeting the requirement. Is it the label? You read it again. The label. Okay. So the question. There's a question about asking the assignment. Okay. Can you see the question? I guess you can. If not, let me know. The question has been asked is what's the meaning of this, meaning the requirement. The requirement means whether the mean amount is this. That is that is what it means. The requirement is you read the English is that whether the mean amount is 5.5. So it's asking this question. Okay. So you can read the whole question, then you will see whether what kind of alternative or hypothesis you want. Is it one-sided or two-sided? So the question is what kind of percentage you want to use. Well, you can, as we said, if it doesn't specify, you can use 5%. It's fine, or you can use 99%, also fine. Because you qualify the statement, you will say you will reject with 1% or 5%. Okay. I hope I answered your question. Someone asked me homework 1 and 2. I think the TA will be released soon. It will be. I'll ask the TA about it. I think on homework 1 will be released, I guess, after, Friday, right? I think on Friday you will release the TA part, and then the peer review part will be after I collect your form, and then will be adjust, and then will be my mark. So that will be that. But probably I will release the overall one, yeah, because that will be the goal. Homework 2 should be fast, I guess, because I think the TA has graded. I guess, but the TA seems to be a little bit busy these days. But I think I will ask. Any more questions? So number 2, number 3, number 4, yeah. So able to look at the solution. As I said, I will try to put the I give you the final short answer for the question. If you want detailed one, ask the TA, because I'm not allowed to release any solution for the homework due to the restriction from the publisher. But you will get, if you want to know, then for the homework, if you curious, you can ask TA now. In case you can email TA to ask now. For those who submitted, but otherwise, I will later put in the short answer to the question. But the detailed answer would have to you have to ask the TA. Okay. Okay. So I guess or we may try to ask the best performed student to release his answer after we got his approval. Maybe that would be easier. Is it easier if I ask the best performing to release their answer, would it be comfortable? I don't know. Let me know. Um, so, any further question? If no, then we are trying to uh, talk about regression. Okay. So this is the last topic, and actually this will be the one that you mostly use. In fact, if you do data work or you do apply econometrics or deal with the things in the real world, so actually ANOVA, a recover and another linear regression beside hypothesis testing will be the most used one. And you notice that hypothesis testing and estimation is underlying behind the linear regression, right? You can see hypothesis testing is behind the uh, ANOVA, but you also see the t-test, f-test in the linear regression too, and also estimation. So everything now we combine all the knowledge in linear regression. So that would be the main goal. Okay, so we'll try to cover half or more than half of this, and then remaining will be covered in the next Tuesday, and then we finish everything. Okay. Um, so let's get started. Again, to remind you what we are focusing on is we're looking at two types of two variable, two continuous random variable, or two continuous data, which is x and y. You can imagine that two distinct variable we are measuring, right? Usually, say the most common thing in economics, you will see in labor economics often is what we call the education and income, right? So it's what we call the uh, wage earning equation. This usually what the data you will see is like you take the education and income, as you may guess, it will be something like this, right? So the more education you have, then probably you will have higher income. Okay. Of course, it doesn't imply study one or two more books will make you more income. I mean, there are various fields to explain why that's the case, but maybe smart people or more capable people study more. But that set aside, uh, you will see, or the age, the older you are, then you get more salary. But set that aside, then you at least you will see having more education actually will make you earn more, right? And that's why when at least when I were young, I mean, maybe different from your, and you always told you study more, then you have a better living, right? So that's the meaning coming from the data study, right? Education actually, more education actually turn out to more income, right? And of course, this is misleading, right? Because usually no one have zero education, right? But sometimes actually you see somewhat here, probably not coming fast, start from zero, right? Um, and the question is try to study the relationship between two variable income, education, or in business application, you want to see advertising and sales, right? So you want to usually data point like this, right? The more ad you do, maybe you have more sales. There will be less or more, but it also depends on seasonal adjustment, right? Christmas may have more, even though you don't do any advertising. So the data you collect in the real world has a kind of random element there, which is not captured in the model, right? In particular, in this case, right, sales is not only depend on advertising, right? Can be depend on a lot of other factors, but we just study the relationship between the two, like the 2D scatter plot we have here, okay? So what we have is to explore the relationship between two things, X and Y, and the data exists in pair, right? Maybe this is one observation, right? This one single person that have look at his income and his education, so it's a paired one, so you cannot swap, right? And also advertising and sales is each data point represent uh, how much the company have spent on advertising and how much the sales generated from the sales, maybe 1 month after or after advertisement has been out, right? May not be the same time, but you can see they're related, okay? So is data point is a closely related measurement in 2 dimensions, right? And you can see that you cannot swap, right? The data you have is x1, y1, right? The second one is x2, y2, right? And you cannot basically just swap them. Then it's an swap x and y or swap any different order would be a different thing. Okay, so that would be clear. And the objective is try to study the relationship. And here we focus on the simplest one is a linear relationship. Okay, we try to see how y related to x. Okay, and here we didn't mention uh, uh, a lot of thing here is a linear, right? But sometimes the data can be like this shape. Okay, it's not really quite linear. Okay, but we don't mention for the rest of this class, but uh, actually you need not regress uh, directly y on x. You can regress on, say, log of x, some transformation, and suppose to regress y and the log x. Okay, then it can be linear. Okay, so you need not get the original variable to get regression. You can really regret on the transform the variable. And why sometimes you transform the log? Because log is the growth rate. So the growth rate. Okay. So if you take log, then that would be one way to handle it. Or you can take square or square root, right? So it can be done. So it need not be the raw variable is y. You need not focus on the raw variable. Okay. You can transform variable. You can consider the growth of GDP, right? So very often you look at GDP maybe growth instead of GDP by itself. Okay, so that is something uh, related, right? Maybe the FDI. Okay, somewhat like this. Okay, um, so for the moment we just focus on uh, a simple which is x explain y is linear. Okay, it's linear. Okay, there's no non-linear stuff. Okay, so the simplest. So if you want to relax this, it will be covered in more advanced class. And basically the more advanced class is focused on if these are relaxed, how we change stuff, and the many things you can imagine, right? Here we have x and y are continuous variable. What if y is not continuous, right? What if y is discrete 1 2 3 4 5 with count data? Okay, how to deal with those? Or if y is not a continuous variable, it's a categorical variable, right? What if y is categorical, like whether you living in, suppose you're doing the choice of transportation, right? Whether you go to school by train, by bus, by taxi, by many stuff, but there's no clear order. So it's no longer a uh, number, right? Then those cases you can still use regression to explain, but that would be more advanced. And other application include that is since we're in Hong Kong, so that is something that you will be explaining. That will be you care maybe the price of the house. Okay, so there's a famous for those who are from real estate. You will be care about price of house, price of apartment. Then this apartment you can explain by it's only flat, right? You can explain the location, what is the height, what is how many bedroom, how many kitchen you have, how many toilet you have, what's the size of bedroom, and those kind of thing, right? You have to explain the price by the feature of the house. So in a technical term that is called people call hedonic pricing model, which basically said for each feature of the house you can run the regression and you can see how you can estimate maybe the flat. I add one more kitchen, how does it affect the price? If I add one more floor up, then what's the price? Why we care that? Because they would give us a good estimate of what the price of the house is. Suppose there's a new flat coming out here in certain area, you build it, then you try to can estimate what will be the price it can be, right? That is very useful technique here. And similarly, you can try to do the estimation for various things, right? Like antique, where something we don't have a market, but you can, based on past data, and do regression, okay? Do some estimation, okay? And the other way you can look at also how the business adjusts the price, right? And probably right? We when for a monopoly, right? You learn in microeconomics, right? You want to go rise the price, right? If the demand is inelastic, right? And if you're going to go down, the demand is uh, elastic, right? Then how you estimate, right? Then you can run a regression on the price and the quantity demand on the quantity sold, and then basically you can estimate the slope of the demand curve, right? Then you can know whether you want to raise the price and lower the price, right? So that's why uh, cut a lot of supermarket and a lot of retail shop often give sales and change prices, and they are actually trying to estimate your uh, elasticity of demand, and then they can decide whether to rise the price or drop the price. Okay, so that is very useful technique. Okay. Any question? So I have mentioned so many applications. I hope that will convince you that when you do your project, there should be a lot of choices you can do. You can study the relationship between two variables, and that is them. I hope you will do regression. That will be the main goal of your project. If I can see that, I'll be very happy. But of course, if you think ANOVA would fit your study better, then go for it. But if you do regression, that would be a easier to think and easier to find topics. But if the data is a regression style, then ANOVA style, then you can still do it. So the data you have is X and Y here, right? The data is a green dots in the scatter plot, and the line is, as you can see, the line is the line with the estimate, right? At the end of the last class, we have seen what do you mean by the line that would best fit the data. By best fit, we mean when you draw the line, you try to make sure that it is the least departure from the data point. What do you mean by least departure? We will define, there's one way to define, the vertical distance from the line holding the x, okay? So for this data point, I hold the same x, okay? I go down, okay, same x. And what's the distance, okay? And because I don't want to make trouble, so whether above and below, or I would have the same treatment. So that's why I would take a square. So when I calculate, I take a square, then it would be easier to handle. So I take a square distance and I sum all of them, right? I will just try to minimize the sum of distance square. Okay, so that's the idea. Okay, by no means that this is the only way to do it. And if you look at other, you learn big data, then probably they will tell you you minimize this perpendicular distance. Okay, that's another type of regression. But for the moment, we focus on the simplest one, that is the most classical one. I'll look at it, how distant x and the y, and why you want to do this way. Because although we run regression, okay, there is no distinction what is y and what is x, okay? We're not trying to, we study the relationship, just draw a line, right? But there's no causality mean here. It's not saying x cause y, but we are saying we're trying to use what we call the variation of x to explain variation of y. Okay, later you will see what I mean exactly mean here, but just to repeat, we're trying to use the variation of x to explain the variation of y. So in that case, you're trying to what we call this y, usually we call the dependent variable. Okay, and this is independent variable. Okay, and that actually true in the experiment where usually you change x to see how the y is impact. Okay, and that's what you are trying to, the error comes from how y is being predicted. Okay, x is something you can control, y is something you want to see. So that's why the distance between line vertical from up from the line or down from the line is something that we care. So we want to minimize that. It's because from the idea that in the lab we can control X, okay, and Y is something that is uh, something that we can't really control that much, is given, okay. So you can see from the very beginning, right, we have more control on the, say, uh, education, right, and how many books you want to study, right, how many years you want to study, is more or less you can control somewhat, right. You may decide not to study further, um, and like then, but the income you earn is more or less uh, driven by other things that you can control, more of control, and somewhat like sales and advertising, right? Advertising is like, as a manager, you can decide how much to spend on advertising, right? But sales is more like you cannot control. Okay, you will try to see how sales drive. So advertising drive the sales. So that is the idea. Okay. Now I hope I have convinced you that X and Y are different thing. Okay, and we try to use the variation of X to explain Y. Okay, so that's why uh, here we have data we have to minimize the vertical difference. Okay, so you can see if alpha and the beta, okay, is, look at back to here, is we are trying, what we are doing here is trying to, this is the slope, right? This is beta, and you extrapolate, this is alpha. And you learn from the high school, right? If for a line, you can always change the slope intercept, right? That's called the slope intercept form, right? Is y equal to mx plus c, if you learn, I think, the high school math, right? So this is the c here, this is m, right? So this is alpha, this is beta here. And by changing different intercept and slope, and then you can describe all the line, right? There's a slope intercept form. Just to remind you, this is the slope intercept form, right? Yes. So this is the line, right? So we are trying to, and if you this is slow, then this, right, this point, right, is given by beta x plus alpha, right? And this is y. Okay, so the distance will be y minus this guy, right? Alpha plus beta x. Okay, so that is what we mean here, right? This is a line. Okay, so this is the line. Okay, the distance between the point and the line is square, so you don't need to worry about up and down. Okay, and you add up all data point, because remember with n data point in square, we call this distance. We try to find the minimum of the minimize this by choosing different slope intercept. Okay, just find the line to best fit everything here, and we'll do calculus. We'll just try to go over the calculus, but we're not going into detail. But this is quadratic negatively on x and y, so you will see the first order condition will satisfy the requirement. But anyway, let's see how we do it. But here is the solution. So we'll derive it. But first, let's look at the result here. Okay, the intercept is given by this, and this slope is given by this one. Okay, tell this slope, if you write it carefully again, then this actually is covariance xy over variance of x. Okay, because you can divide both sides by n or n minus 1, depends on sample or you count the population, doesn't really matter. Then the idea here is look at covariance, right? Remember, is how x and y move together linearly, right? Variance is try to make sure that your term are normalized by the x, because x different scale, I want to scale it down. Okay, so basically it's how it's related to covariance but normalized covariance. Okay, you can see beta is a somewhat a scaled covariance. Okay, turn out to be, it's very interesting, right? So covariance is reborn here, right? So somewhat. And look at what the meaning of this alpha this, right? We write in this way: y bar alpha head plus beta head x bar. Okay, so you can see from this is very similar to this equation, right? So that means that if you have this best intercept and best slope, okay, actually the line would go through the mean, okay, would go through the mean x bar y bar. Okay, so that is the implication of this. Okay, you go through the x bar and y bar. Okay, so that okay, so that is the idea. Okay, so you find the best line, turn out to be the line will pass through the center of data, which is x bar y bar. Okay, so let's again see graphically what do you mean by here, right? So there's a data above is blue, below is red. Okay, and regardless of what you draw the line, it must be the case that you pass through the center of data. Okay? Suppose this point is x bar y bar. Okay, and we pass through this one. Okay, and what should be the slope here? The slope here will be given by covariance xy and variance x. Okay, so this will be the slope. Okay, so if you are Excel, you given data x and y, bunch of data, right? What's the slope? Okay, you can basically tell Excel, I want to calculate variance and covariance, then divide it, then you're done. Okay, that's how you can do that part. Is that okay? Before we go to proof, so that is the idea behind. Okay, if no, we'll try to very quickly go over the proof because it's somewhat algebra, and because we don't rely on the calculus, so I just very briefly go over the calculus here. Is this is square, right? So let me quickly see the math here, right? yi minus alpha minus beta xi. So to do this calculation summation, so we do the chain rule. So alpha, okay. So that will be you doing the chain rule. So it will be summation, doesn't change. You can differentiate this with 2 times yi minus alpha, the chain rule, right? So then you will be, you differentiate with respect to alpha, then it's -1. So there'll be 2 here. So that's why you have this, okay? For those who don't know calculus, fine, you can forget about it. Okay, the same idea when you differentiate beta, okay, that you will have 2, this according to the chain rule, okay, and then you define beta, then it will be negative xi, okay. So when you set to 0, that's how we have these 2 equations. But as I said, if you don't comfortable with calculus, you can forget about it because just give you some taste of how this thing be improved. Okay. And the important step is trying to tell you is from the first equation, you can prove y it passed through the center. Okay. So you will see summation of this. You can divide everything by n. Okay. This will be bar, and this is with n alpha head, but the n alpha head. Okay, and this one will be beta head, and the sum of x over n with x bar equal to 0. So we write and give you this one. Okay, so you can see here the first thing is if your regression has a intercept, then you pass through the center of data. If you don't, then there will be, you will not. Okay, if you consider that the case where the intercept is, you don't want to intercept, then that will not be the case. Okay, and second is here is I try to the beta, right? I just rewrite it. Okay, and what I'm doing here is I put this inside here that gives us this C1. Okay, and is that okay? Then we go to the next slide. Okay, here is where we will put, we separate them. Okay, put this y one side, x to the other side. Okay, so that we will have this one. Okay, and now we can put the beta down. It just basically is making beta subject, right? So basically your beta head here, get the beta head out, and then just you can see here. And this form doesn't look very nice. Okay, so because this is easy to calculate, might be, but this is more easy to think there's a covariance over variance. Okay, and the rest of this last slide we were trying to show you actually the same. So the denominator, okay, same as this denominator, this numerator. Okay, the proof is very elementary. Oh, what's the cap here means? Okay, so this this notation, we maximize this, right, as, okay, and when we say FOC, okay, that means that we want this, the derivative, okay, evaluated at alpha equal to alpha hat, the particular value, the optimal value is equal to 0, and the same thing here. So yes, alpha hat is what we call the optimal alpha. Alpha can be very value. Beta hat is the optimal value. So that is a standard notation when you have calculus. So this is particular value because only at this particular value this is 0, and it's not a random variable. It's an unknown somewhat, like here we use different alpha as a kind of, we choose different value, and here we say this variable evaluate at this particular value is unknown, it's a value, it's unknown constant, and this is a variable. So that hard to explain, but this is the standard notation. If you don't like, you can just say optimal alpha. I hope that would make sense. So just explain the denominator. Very good question. So if there are any question, please feel free to stop me because I just a little bit fast because this is calculus is not required, but I just try to give you some idea. Okay. And what I want to show you is just to do simpler thing is you try to prove this equal to this one. Okay. The reason is we have complicated version, I can just eliminate, then we go to the easier version, right? Instead of course I can go backward, but this is easier way to think. Okay. This, okay, can be written in this way. Why? Because here, right? So I can use this multiplied by that guy and this multiplied by that guy. So this is this beautiful law of multiplication, right? So we can divide in two parts, okay? And the first part, only the first part is relevant, okay? You can see at the end, only this part remain. Why that's the case, right? So you can take this x bar is independent of I, so you can take it out. So that's why you can see here. And here is the summing up all the data point different from the x bar with the mean. So this must be 0. The reason is you summing this, okay? And okay, you sum this. This is summing all the bar will be n prime, okay? So n bar, and they're the same, right? Because this is equal to summing all the data over n, okay? So they're the same thing, okay? So that's why this is 0. Okay, so that's why equal to this. And you can use the same proof. You can just replace this by y, okay? And you can show this is the same idea, okay? So that's, at the end, we have proved y beta hat is covariance xy over variance of x, okay? So that is something that you should keep in your mind from this class. I hope if you can't remember any formula from this class, at least you can remember this formula. That would be a nice formula to remember, I hope, because this is somewhat the idea behind. Because I think the most important from this class is regression. And the simple linear regression is something that you want to remember, and you want to remember this is how to calculate the beta, how to get alpha. All right, alpha hat the the intercept will be just y bar minus beta hat x bar. So this is something that I hope you can remember as the something if you really want to remember something. Okay. Any question? I hope I explained this regression. And is that okay? So this is just showing you that without any statistics, okay, just mechanically, if I want to find a line to best fit this, what should be the result? Okay, this is the just least square method. It doesn't say anything about statistics. There's no probability here. Okay, it's just mechanical algebra. Okay, and then you can see why calculus is needed, because you want to maximize and minimize. That is the meaning of calculus. Probably most of you would, some of you may know it. At least you don't know how to operate calculus, but at least you know calculus is the way to handle this kind of situation, maximization, optimization. But anyway, let me continue to give you an important result before break is to stay you the thing we have done for the alpha and beta. We say beta is covariance over variance and alpha given by this. Actually, you can still have a nice property according to the following model. Okay, this is called classical OLS assumption. Here is the following. Okay, so you would say the y data y is generated from this data. Okay, you assume maybe say income is determined by something, and that will be affected by your education. Okay, maybe this is a premium for each year you in school, right? Plus some other thing, other factor. Okay, some random factor. Okay, and this is some constant. Okay, you may consider this constant is the minimum wage, right? Alpha is minimum wage, right? And beta is how the premium that you get one more year in school, right? And there's some other factor, right? Maybe by luck you are getting a better job, right? Or you happen to have lucky to have a work for a nicer employer, okay? And this is called error, okay? So this is the classical assumption, okay? Classical say the model is like this, okay? Underlying behind is simply the y driven by x in this foreign form, okay? And the next assumption is a little bit tricky in economics. It's okay in experiment where you can control x, okay? Or x is rather unrelated to the generation of y, okay? What does that mean is in classical assumption, they are non-random, okay? And in one study, what you will see, what it means is the covariance of x and epsilon is 0. Okay, they're uncorrelated. But anyway, we are not focusing on more complicated one. The classical one just said X are more or less controlled in the experiment. So the most challenge from regression, as you study later, actually you will see how to make sure that X are relatively non-random. Okay, it's exogenous. It's a very important thing. But we're not studying this. But anyway, we just say they're non-random. Okay, this looks pretty trivial, but this is a very important thing to check. And here, this if you write this model, then you can put if it's non-zero, then you can put everything in alpha. So that's why this random variable, random is a random variable, have zero mean and the same variance. Okay, zero mean I think is not an issue because if there's positive mean or negative mean, you can put everything in the alpha. So that's not a big deal. The more big deal is the same variance assumption. Okay, that is the technical term is called homoscedasticity. Oh, I forgot how to spell. Probably can check the book. Homoscedasticity, the same variance. But this is the classical assumption. So this one can be relaxed somewhat. It's not a big deal. But for the simple model, this is the assumption we have behind. And the errors are not correlated. So that's something, what it means is we don't observe other stuff that we don't model. So remember this error term is that means someone we didn't model. And what it said is some within model are not correlated. Okay. If they're correlated, then that is a problematic thing. Okay. So what might be correlated? So a lot of time when you look at data as a time series data, there's a problem. Say, remember your data about sales and advertising. Okay. And this, an error term can be an issue because error term may be the capturing the random error term, by capturing, say, repetition, word of mouth. In those cases, this will be correlated. Okay, because the more people like your product, and then you will promote more, it will be related in that way. Something we don't capture. Okay, and if over time, then they will be actually related in terms of time. Okay, but for if you have cross-sectional data, it also may have issue, right? Because suppose you have you're collecting the sales data, it's like the Hong Kong Island, okay, Hong Kong Island, right? And then you have maybe you have a store here, store here, store here, store here, store here, right? And you can imagine that store in the neighborhood may be related, right? Maybe here have more sales and surrounding may have more sales, right? Or if here have more sales, surrounding have less sales, okay? So somewhat they're related, okay? In that case, even cross-sectional data will have some issue here, okay? And also when you look at the housing price data, right? So if there's a new building built there and a new flat being sold, and that will depress or promoting the price nearby, right? So that will be this unmodeled element, okay? You need to assume they are not correlated, okay? So this not easy to solve, but suppose all this restricted assumption is being matched, what you will see, okay? Of course, this can be relaxed, but for our purpose, we don't, okay? That how to relax them will be something higher level up you will learn, but for the moment, we just have everything there. It's very restrictive, but assume this is all right, okay? This is an second important theorem that we don't prove in our class. It's called Gauss-Markov theorem. You can see Gauss, right, and Markov, right? Both are very famous mathematicians. Okay. But anyway, so what it that mean is the thing we have figured out in the previous slide, right, is covariance xy over variance of x. Okay, and this come from y bar equal to alpha hat beta hat x bar coming from this. Okay, turn out to be this unbiased estimator of alpha and unbiased estimator beta. Okay, as long as you're willing to assume the data generated from the assumption one. Okay, so what you do here is exactly the unbiased estimator. So that's good, right? If you believe that's the case, then we're done. And turn out to be this is the also the best, means the least regression, sorry, least variance. If you consider uh, the estimation is based on linear in x, okay? Linear in x is just like, suppose you say alpha and the beta is a somewhat function of x, x1 plus x2, whatever, and same beta is also this. As long as you consider linear estimator, linear in x, uh, then that would be best. Okay, but anyway, you don't need to care about all this, but just saying that they are unbiased and also good in some way. Okay, that is something you remember is a somewhat good about this is called blue best linear and biased estimator. Okay, so um, so you have a linear, you don't have any non-linear term, so that's what bilinear. But anyway, you don't need to worry about the exactly meaning of this. It's just like basically it is good if you focus on a particular way to estimate. Okay, I guess I should have a break of 15 minutes. Let's resume it 1:37. In the meantime, if you have any question, then you can just leave in the chat.
뭔 소리인데?
So I've received a question during the break. that asks again, what is the difficulty level for the test? Let me repeat again, it will be similar level to the past exams, because I don't want, it will not be more difficult or more easy or more difficult compared to exam in the past. So you'll be somewhat, sorry, at that level. Sorry. And that if you try to look at the questions, they will be similar to what you're expecting in your homework also too. So you'll be somewhat similar in terms of difficulties. Okay, so let us continue our work. But before we continue, any questions? So so let's repeat it a bit. Before the break, what we covered today is so far is a scatter plot, right? X and Y, and then we know how to minimize the distance, vertical distance. Is this a formula? And we show that if you follow these classical assumptions, okay, which have a lot of restriction, maybe 1 is okay, but 2 and 3 and 4 is a little bit issue, okay? Sometimes you may don't even think 1 is fine, but anyway, 1 is the least problematic thing, but 2, 3, and 4 is a little bit not sure. And we know the Gauss-Markov theorem said that would be the best estimate, and then if you focus on linear combination on X, then that would be the best. But this is what you call the best linear unbiased estimator. But anyway, so now what is the interpretation? Okay, interpretation. Okay. So interpretation, once we run the model, right, we have estimate model, we have alpha head and beta head, right? And X will be the what we have, right? And then give the X, I will give you a Y, right? Some kind of predicted, okay? So give me X, I can try to explain the Y, right? Try to use X to explain Y, okay? And but it's not saying that change X will cause Y, okay? Because it's not saying that X cause Y, right? Because it is entirely possible that there's underlying Z that actually affect both, okay? We just said when X move, Y also move. It's okay, they move together, or co-movement, what we call the co-move. So first is, what is alpha head? Alpha is intercept, right? So it's very easy saying that was average of the value of Y where X is 0. Okay, what is basically is expected Y given X equal to 0. Okay, so that is what exactly mean by alpha head. And do you know that this only meaningful when X has any value around 0, right? If X has value like most of the data is above, say, 1000, then X near 0 doesn't mean anything. Okay, now look at the data, say the labor market, right? Income and education, okay? And under Hong Kong, we have compulsory education, like many different cities in the world, right? Where you have at least, 6 years or even 12 years or 9 years of education, okay? So in that case, the intercept actually doesn't mean anything because, it means a lot because you don't have actually any people have 0 education, right? So that's why you only make a lot of sense when we have X is around 0. So is there anything special? Only if the data is around, okay? The second one actually is most important. Actually, we care the most is the beta, right? What's the meaning of that? So it means the slope, okay? It means on average, if X increased by 1, how much Y would change, okay? Do note that the beta can be positive, can be negative, right? So basically, X increased by 1 and how Y would decrease or increase, okay? But remember, it's not causation, okay? Which means that it's not, you change X, Y will change because there will be Z underlying to change both of them, okay? Because this is maybe education, right? And this is income, okay? But this may be ability, okay? And getting smarter actually will increase your income and also increase your education, okay? And it's just association, okay? So you notice that this is a variance of y associated variance of x, or explain this sometime. Because if you run the regression, instead of x and y, okay, you use y minus y bar and x minus x bar, okay, you will have the same regression, okay, for the beta, okay. Of course, alpha would then be 0, right? So you will get is, okay, that's the regression you get, okay. So that means is how is distant from the mean, okay, explain the deviation from mean for y. So it's deviation from mean for x to explain deviation of mean from y, okay. So it's a variation of y explaining the associated variance of x. That's what it means, okay. So that is what we mean here. So I hope that would give you the interpretation. So just make sure that it's not causation. That's the most important part. So it's not causality. If you read the textbook, then you will be more clear. But I hope that gives you a better understanding on this one. Okay. Any question? I hope that is clear. So the next part is what we call residual. Okay. Oh, so ask me explain causation. So what I mean is this, we run the regression. What we want is we try to use the variance of x to explain variance of y, but it doesn't mean that x cause y. There's no causality here, okay? Because as I said, x changes and y changes, right? But it doesn't mean x change x will change y, because we didn't exclude that actually there's underlying z affecting both, okay? So it doesn't mean anything whether you increase x will lead to change in y. But saying that if you observe change in x, then there will be associated change in y. Okay, so that is the idea. Because there's no, with this, it's not enough to say causality. You need more evidence. Okay, it's not saying that this is not enough to draw, but it is not. It is saying that we only observe the association. Causality have to be derived from other thing, like suppose you can change x by yourself, then observe y, then of course there will be causality. Like experiment, right? Like the drug experiment. You put this drug here, you put that drug here, you don't put drug here, then you see a difference. Then you run the regression, then you can say causality. It's just the statistics. Here, you cannot prove causality here. Okay, you need some more thing to establish causality. Okay, but that is what I'm trying to say. Okay, you need more than what we need, more evidence than what we've seen here to validate this. Okay. So error. Okay. So error is defined as in the model is this one, right? Because the model is yi alpha plus beta xi plus epsilon I, right? And we call this error. Okay. And this is a random variable unknown. Okay, we don't know this. Okay. But when you observe x and y, okay, and then you estimate alpha hat and beta hat based on the formula, then you can calculate some what we call residual, okay, which is calculated by the actual data, right? Look at the y and minus the yi hat, which is common line, basically just the line, you dot the point, and this is called the residual, okay, is the can be positive, can be negative, depending on whether you're above or below, but that would be the residual. Okay, the residual is something that realized it. You can say that someone can realize error, you can say, but the error is a population thing. It's something. It's a random variable. Okay, so why we want to care about the residual, right? Because the residual is a realized error. So we really want to estimate the sigma square. Okay. Later you will see why we want to care about sigma square, but suppose we need to care about this one, sigma square. Okay. And how to estimate the sigma square, right? Remember, sigma square is this, the variance of epsilon I is called sigma square. Okay. Sigma I. Let me write it down here again. Remember the formula is variance epsilon I. Okay. For every observation, the random term has a zero mean, right? This is called error, zero mean, and the variance is sigma square. Okay. Then how to estimate this guy? Okay. Same as what we learned. This is this minus zero because the mean is zero, right? So this minus zero square over, okay, yn minus 2, okay, no, n minus 1. You can explain by degree of freedom because we have estimated x bar and y bar, okay? So we have estimated two mean here, or we have two parameter here, estimate alpha and beta. So that's why you have minus 2, but that is explanation, but I don't think we go into detail for this one. Yes, we don't explain why this n minus 2 actually can be explained, but I don't think it's out of scope to explain why this is actually a biased estimate. Anyway, so that's the definition. And the standard error is you take the square root of this. Okay. So that would be the definition. So just bunch of definition. So there's nothing to whether you understand, but whether you know the definition, you know the meaning or not. Okay, why we care about this? Then later you will see why we want to estimate this one, because with this we have a lot of things to say. Okay, any question? No. Okay, we now explain why we need all this here. Okay, so remember again, the model is y equal to alpha plus yi equal to beta xi epsilon I. Okay, and we set this is 0 and variance of this is sigma square, right? And do note that the alpha and the beta, okay, are coming from x and y, okay? And x is exogenous, right? We are non-random, but y is random. It's driven by this, right? So the value of y, when we do the sample and different sample, we have different y, right? The x, maybe you know it, okay? But the y will be different each time, okay? So then that means that when you calculate the alpha and the beta, which depend on y and x, right? X you can decide, but y is, you can imagine y is drawing from this machine, right? Give me the x, you will, based on the unknown alpha and beta, you will generate y by adding some random term, okay? And we want to estimate alpha and beta, okay? But the fact that y is depend on some random variable, which means that alpha and beta also random variable, okay? Because y is a random variable, okay? That depend on the epsilon, okay? So because these are constant, unknown, this is determined, you can decide what it is, there's no variation here. So the only variation is here, okay? So the variation here is given by this sigma. So if we know the sigma, okay, then we know how alpha and beta will look like. Okay. And what I mean here is we will show, okay, which we try to do in the technical part, is we can show how the intercept, the variation of the intercept, the variance, okay, is given by this complicated formula here. Okay, it's just if we know the sigma square, okay, we know the sample size. This xi is, we know it, we choose it, okay, we have that, okay, and we can estimate this alpha hat. Why I keep alpha hat? Because we can do whether alpha hat is bigger than 0 or equal to 0, right? We want to check, or less than 0, right? We can do hypothesis testing, or we can do interval estimation. What is the intercept? Okay, so they're important, right? Just like if you are the manager, right? You want to see how advertising affect the sales, right? You want to see, even though if you don't advertising, what would be the sales, right? That would be important, right? The baseline, right? Somewhat we want to estimate those as somewhat important. Okay, so let's see. Okay, and usually if we assume this is normal, okay, which is a okay assumption, because you can imagine the central limit theorem applies, because you can imagine this error term is the average outcome of many things affecting. Okay, so central limit theorem can apply to say the distribution is normal, because usually the error term, okay, is affected by so many things we didn't model, right? And those things is average result is captured by this epsilon. So so that's why it's okay to assume normal. But once you assume normal, alpha and the beta will follow a normal distribution. Okay. Because alpha and beta are the linear function of y. Okay. And which we don't prove here, but actually you can easily show. But if you have this, okay, then that will alpha hat will have a normal distribution with alpha. This is come from the Gauss-Markov theorem we just said before the break. Okay, and this is coming from here. Okay, normal. Okay, and we usually we call the standard error. We take a square root and replace this by s. Of course, take a square root, so it's sigma. Use s to replace the sigma, and everything will be in terms of data. Okay, so this is the idea behind. So let me show you the quick proof why this is true. Okay, we do it very quick because I guess it's not the main concern for us. Okay. So remember, x is exogenous. Okay, so let's define Sx6 is the sum of square total. I mean, on x, you can imagine sum of square on x. Okay, and the alpha is defined by this is the formula here, right? Alpha is this one. Okay, and what we do here is we replace y bar by its definition, sum of y over n. Okay, and here is difference of beta, right? This is covariance, the sum of this and over Sx6. Okay, I just simplify. Okay, and what I do here is I take the, remember I can forget about the y bar, right? Because this is we have proven this, right? This is proved to be true. same as you forget the y bar. Okay, so only yi here. Okay, and you pick up the yi. First one give 1 over n. The next one gives you this times this here. Okay, you take the summation out. Okay, and because y is a yi, right, is alpha plus beta xi epsilon. So these are constant, and we have said covariance epsilon I, epsilon j are 0. So the variance, some variance or sum is sum of the variance. So you can take the variance inside, okay? And because this is a constant, you can take a square. So that's what you have this guy. Okay. And how do you proceed there? Okay. And so this is the last step here. Okay. How do you continue? Okay. This same as this one, because variance of yi, right, is variance of alpha plus beta xi plus epsilon I. And this is a constant. The first part is constant. So it's variance of epsilon I, so which is sigma here. And this is just completing square. Okay. So this from here, you just a minus b square is a square minus 2ab plus b square. Okay. So this a square 2ab plus b square. Okay. Minus a square b square 2ab. Okay. And now this guy, now use other color. This guy, in fact, is sxx, right? So you can eliminate one out. Okay. And here, xi minus x bar, we have shown this is 0. Okay, so that guy is gone. So that's why you only have left first and a second, but you summing all the 1 over n, so there will n of 1 over n squared, so it's 1 over n. Okay, so that's what is left here. Okay, and the one more step is just making common factor. Okay, and this is sxx. Okay, and this n. Okay, and here you are just using the completing square method again. Okay, a square minus b square will be this minus xi x bar square. Okay, summation. Okay, and your summation there will be okay, let me do it. You do this will be, actually we've done it many times already. Okay, so then you will together with this end up with they cancel out, because there's one term here, subtract. So that's why we have this one. And this is the formula we prove. Okay. As I said, just a little bit tricky, the algebra. I mean, the algebra is not complicated. Just there's some more math behind. But I guess since most of you are not interested in this, so I would just go a little bit faster. In case you're interested, you don't follow, then you can ask me after class, I guess. I just save the time because, as I said, we lost one class due to the configuration next first day. So we need to be a little bit, hurry up a little bit. So now we have t-test now, okay? So we want to do a hypothesis testing, okay? So that's a key thing we want to know is whether alpha is equal to a certain number, okay? Not necessarily zero, but we want to test this, okay? But we want to see whether the intercept is equal to a certain number, right? And what to do is there's a t-test, right? T-test is just this minus what you try to do, and then you just over the standard error, okay? It's t-test. And the algorithm n-2, we don't prove it. But if it's not equal to, then you do two-sided test. Okay, I hope now it's rather clear. Otherwise, you do the one-sided one, depends on what you do, okay? So this is the hypo testing. I hope that is rather straightforward. And what's a point estimate, right? This is the beta, right? This is beta head. Okay. The point, why this point estimate? Because this unbiased estimator right? Unbiased estimator for alpha, right? So this is the good estimator, and the width of the, oh, sorry, that should be marginal error. It's marginal of error. It's not with interval they multiply by 2, so it's marginal of error. Okay, it's this guy times this. I think this is, you know, very well. Remember, the only difficult part is n-2. Okay, so that's what you have is alpha hat Tn minus 2 alpha over 2. Sigma is standard error is SE times this guy. Okay. So I guess we can continue to talk about the beta. Okay. So it will be the same idea behind. We are going to show the beta. Okay, this is the most important thing in the regression, because once you run the regression, you have alpha, beta, x, right? You really want to check whether beta is equal to 0 or not, because you want to see actually the two variables are related at all or not, right? So that's the most important test you want to do at the beginning. Once you run the regression, you want to check this one. This is a very rather standard thing to do, where regardless of the regression, okay? Basically, just same as ANOVA, right? Testing whether this is a meaningful at all, okay? So what we're going to do is, if you assume this is normal, and then what we have is the same thing here, we just replace this here, put in here, because unbiased estimate, right? Because this is coming from the Gauss-Markov theorem, okay? One is normal because beta is near function of y, right? And standard error is replacing sigma by s. This is rather standard, okay? I'm not going to detail for each because just a bunch of formulas here. And here we want to prove beta, which the proof will be much easier because beta is a linear function of y, okay? So let's again make this notation SXX, okay? And this beta will be equal to this, right? It's just replacing what it means, okay? And we know that this x is unrelated to y, so we can take it out by having a square. And x are the same, you can put it out. And And because of the, again, the yi are uncorrelated, right? Especially epsilon I and epsilon j have covariance that is 0, okay? So it means my covariance of yi and yj is also 0, okay? That means that you can, variance sum will be sum of the variance, this constant can take out to the square, okay? And variance of this is a constant, so you can ignore it, okay? So that become variance of yi, it is where epsilon I will be just sigma square. So that's why here, and this is basically sxx, right? And you cancel out the square term, so that's left with this one, sigma square over sxx. Okay, so that is the key of the proof, but as again, that will not, the proof will not be very important for our purpose for now. The important part is here. Okay, you want to do hypothesis testing, but the beta, you want to see beta is within some number, usually is 0, right? But that sometimes it's not 0, okay? And based on the past study, you want to see whether beta is what number, okay? So again, you try to do this t-test. Two-sided one will be n minus 2, okay? Okay, and the point estimate, okay, the beta hat is given by this, we know it, it's just covariance xy over variance of x, so this is not within the row, this is again the marginal error. Okay, will be this one. If with interval, you have to multiply by 2, but we just with error, the marginal error. So it's beta plus minus this guy. Okay. So I'm not continue to do it because I think your mind is overrun. But I want to show you how can we do regression in Excel. That would be, I think, is most profitable here. To spend the rest of time is to show you how you run the regression. Okay. Can you see my Excel screen? So now suppose you have data x and y. Maybe you can imagine x is the income. Sorry, y is income, x is education. But anyway, we just try to have two generic data here. Okay, this data point. Suppose I have data like 1, 2, 3, 5, 8, 7, whatever number you want to put in. Okay, I don't know what it is, but just some number here. Okay, you can make longer or shorter, doesn't really matter here. Okay, so there's a bunch of data, this x and y. So we want to run regression. Okay, we want to estimate, say, beta and alpha. Okay, so the first thing you want to do, maybe you want to have the mean of x and mean of y, right? Because that will be used, say, maybe mean x and mean of y, right? That's easy. Mean of x is just average, okay, of this x. Maybe I use the formula. I hope that's okay. This is data, maybe highlight data by putting some color here. This is our calculation mean of x and mean of y. I don't think that would be an issue for you. There's up until now, you should be able to see how to calculate mean of x and mean of y. Okay. Maybe I put slope. Okay. Intercept. Okay. The slope will be just the covariance over variance. Okay. Covariance. Either use P or S, doesn't matter. If you use P at the numerator, then use P. Okay. I use P because it doesn't really matter anyway. Covariance over the variance P. So over variance X. Okay. So of course you can use the, let me show you. Alternatively, you can use the variance S, the same thing. Covariance S of the two over variance S of X will give you the same answer. Okay. And the intercept can be found by, remember the formula will be y bar minus beta x bar. So it will be this minus this times whatever you put. Okay, this will be the intercept. Okay, but there is a, although you figure out this is rather simple to do, but luckily Excel has a rather easy way to do it. You can call slope to find the slope, and have a slope, and then you put the y and you put the x, then we're done. So you can do this, or you can do directly, or you can do the slope. Here also we have intercept. This, do note that this function only available in the recent version of Excel. In the old day, you don't have this, but now we have very convenient function. Okay. Up until now, is there any question how to do the regression? Okay. So I want to show you the last thing of this class is we can do something same as ANOVA. Okay. So you go to same as do ANOVA, which means go to data and data analysis. Go to data and data analysis. Then you go to the very end, you go to choose regression. See regression here. Click regression, okay. Okay. Here comes out the regression input. Okay. So input range of y, so you just pick the y. Okay. You can include the label, doesn't really matter. So the label of y, I put B, column B here. And label of x, I put column x here. Okay. And because of label, I put label. Okay. Constant is 0, I don't do it, usually don't do it unless you some reason, so just ignore this one. Confidence interval you can 95, okay? And now you can just output range, you can choose where to output it. You can put it here, say. Okay. Okay. Then you end up with something. Okay. The first part, some of this statistic we'll explain in the next class. We'll give you the idea what's behind here. Okay. And also the ANOVA, we will do it next class. Okay. But what this class cover, oh, I don't need these two columns, sorry. So what we have is with coefficient, standard error, which we have just shown in the slide, and the t-stat, we show you how to do it. You can do p-value, right? Because this is just the two tail test, the two tail value, I think 95%. You can also have the confidence interval here, okay? So you can see the intercept, both intercept and x, is not significantly different from 0, okay? So basically you can conclude that x and y do not have a strong linear relationship, although seems to be related, but you cannot see they are related in terms of linear one, okay? of course, you can, the first thing you should do to the data, you should actually draw the scatter plot to see how the data looks like. Okay. You may expect there's a good linear relationship, but in fact, it's not strong enough, right? You may imagine that there should be a line here, okay? But in fact, data tells you maybe just this one is sufficient, right? You don't need this line. Maybe a horizontal line is also can do the job, right? So the X actually can't help you too much, okay? So I guess I overrun. So I think this is what I want to say today. So have a nice weekend. I guess I will see you next week. Bye bye. Thank you. So I'll stay around, answer any question you might have. No, we don't have quiz on next Tuesday because we haven't finished the regression, so we don't. So don't worry, there will be no quiz. Just we'll finish everything next week. Bye bye. Thank you.
Professor。
OK。
係，我想問翻 hypothesis test 嘅嘢得唔得啊
？OK， 你問啦。
我想問both tells 睇翻佢個碌士咧，佢有一個例如 t test both tells 佢嘅 t value 係-2啦，跟住
等我揾翻啦。你
佢係
講
33個碌士33。
33大概係大概呢度係嘛？
個畫面你冇轉到。
哦，係咪呢度？
係即係我想問點解佢scenes 嗰度咧係寫細個，係咪意思佢
absolute value 細個？
即係佢雖然係係咪即係當 both test 就當 focus 喺 right tail 嗰度，跟住
需要你咁樣做啫，你只係。
所以係咪即係當佢係2咁樣計？雖然佢係
計呢個位啫嘛，其實一樣啫嘛。你2.13喺度嘛。但係你可以睇成直接喺，即係你通常我哋計下個 T 係咪極端過嗰個 critical value， 極端過咪 reject， 唔極端過咪唔 reject 咯，因為你都係咁樣睇啫嘛。Is it further away from zero or not？ 呢個係你個 critical value， 即係呢個係你嘅 test statistics 嘛。你唔明喺邊個位置？你係唔明我呢個點啱寫係嘛？
點解係寫細喎？唔係寫即係如果當
我以為 negative， 你可以咁講嘅。
點解可唔可以寫大過？因為佢-2係正常，即係當佢係-2。
我哋可以咁寫嘅，因為你係呢個係大過呢個呢個 critical value 都得冇問題，但係 critical value 係負噶嘛，或者大過呢個負2.13都可以冇問題，一樣啫。
如果咁我到時咁寫，我即係佢寫 T 大過等於 T15。
通常我哋為免麻煩就唔睇咗個，到家都係睇正數咯，睇正數簡單啲。
即係直接當嗰個-2係正數，直接2咁樣同嗰個2.13、145咁。
係啊，咁樣簡單啲，但係隨你點用都冇問題嘅。
即係合理就 OK 啦。
合理就 OK。
同埋到時係咪即係話你有兩個方法，一係用呢個嚟做比較。
一係你 A， 一係 B 咯。
即係到時寫一個就 OK 㗎啦。
除非話俾你聽要你用邊個咯，如果唔係你邊個，如果冇寫明你就用邊個得。除非我話用 P value 方法，咁用 P value 方法。如果我係話 critical value，critical value。
好，唔該晒。
Okay, there's another question. Why I see no relation from data? Okay, so let's go back to the Excel again. So why I said there's no relationship because you check this p-value. P-value is not less than 5%, right? So that's like, it's not different from 0. Okay, actually you can see from here, the critical confidence interval actually includes 0. So you cannot say that there's no linear relationship because it's not different from 0. Is that okay? And also hypothesis testing. What we also usually use the null is always why we want to use null. Null is always equal in our class. The reason is because we are analyzing under the null, so that's why the same you say if one side is okay when you say that one, but usually we do in this way, which is I think is the more correct one. It doesn't really matter, but we just try to understand why under null what it means. It's more accurate, but okay.
Professor，
Yes，
你話個 P value 係0.117，即係大過0.05啦。
咁即係唔會啫咯。
即係你當咗個 B 係即係嬲嗰個係 B 係0啊？
哦，呢個係咁樣，Excel 出就係咁樣噶啦，佢係當0咁計。
哦 ，OK，
呢個自動係計0嘅，即係如果你係做0，咁咪咁樣做0咪直接出呢個咯。呢個係有出呢個就係呢個係beta 等於0，同埋 beta 唔等於0。
哦 ，OK。
仲有冇問題啊？大家有問題請講有問題可以問。If you have a question, please feel free to ask. Any more questions? Just wait 1 more minute. If there's no further question from you, then I'll end the section. Okay. Since no further question, then let's end the meeting.